Live from the Stability and Trim for the Ship's Officers podcast studio, where the vessel's its own best instrument of stability and trim. Welcome. This is William George. Well, welcome back. This is podcast 21, and it's chapter 10. We're still on longitudinal hull strength, and this is part 3 of chapter 10, and we're at page 232. The shear and bending moment diagrams. You have seen that when the force of buoyancy acting upward is greater than the force of weight acting downwards in the midship section, which means that the force of buoyancy at the ends is less than the force of the weight at the ends, the vessel tends to hog. This illustrates the general way the principle that bending moments exist due to the difference or differences in the forces of buoyancy and weight along the length of the vessel. Therefore, in finding the bending moment for any given condition of both weight and buoyancy distribution, you must find the exact extent of the force of the weight acting downward and the exact extent of the force of buoyancy acting upward at all points along the length of the vessel, and then find the difference between these forces. Plotting the differences in turn will reveal the extent of shear stress and bending moments existing for a given condition. These principles can be illustrated by the following simple example, and we're looking at figure 10-7 on page 233, and we're in the 4th edition of Stability and Trim for the Ship's Officer. The caption of the illustration is a floating body construed in a series of 6 boxes. Okay, suppose that the floating body is constructed in a series of 6 rectangular boxes, each measuring 1 foot by 1 foot by 1 foot, or 0.3 meters on each side, and each connected by and to with a thin strip in such a way that the blocks varying weights can be made part of a floating body in any combination. So these are like strip joints that connect all the boxes together so they can move vertically. Now in figure 10-7, consider a combination of blocks designed as condition A, which is at the top of the diagram. In this condition, the floating body will consist of 6 blocks, all weighing 36 pounds each. Connecting the blocks by and to the side strips and placing the body in salt water, note that the body floats with a 0 trim, and the draft somewhat about half the depth. The weight of the box is 6 times 36, regarding the displacement of the side strips, or 216 pounds, while the floating body, if fully immersed, would displace 6 by 64 pounds, or 384 pounds, leaving a reserve displacement of 168 pounds. It may be observed that the weight of each block is opposed by an equal buoyant force, since there is no difference in weight and buoyancy at any point on the length of the body. No load exists on the body, and no shear force or bending moment exists. This may be clearly seen if the blocks are disconnected from the side strips and made separate floating bodies, loosely connected by the side strips. Each will assume exactly the same draft, showing clearly that no vertical shear force exists between the blocks when they are connected. If no vertical shear force exists, no bending moment exists either. Now, imagining that 2 60-pound blocks are substituted for the 2 midship blocks, 36 pounds of floating body. The 4 end blocks are 96 pounds, and each of the 2 middle blocks are 60 pounds. Each are inserted loosely between the two side strips, and it seems that the two 60-pound blocks assume a draft almost equal to the depth of the body, while the 36-pound blocks, of course, float as they did before with a draft equal to little more than half the depth. It is clear to see that the vertical shear force will exist when this combination of blocks is connected by and to the side strips. Also, there will be a tendency for the body to sag, indicating the existence of bending moment. In Figure 10-7, this combination of blocks will be designated by condition B1, and drawing the shear and bending moment diagram will attempt to ascertain the exact extent of the shear forces and the bending moments of the floating body and in this condition, and that's on Figure 10-8 on page 235. So in 10-8 on page 235, this is the shearing bending moment diagrams for condition B1. When you look at the upper shear strength condition, there's a weight and buoyancy curve for condition A, and the weight and buoyancy is equal along its uniform length per unit foot. So there is no shear force and there is no bending moment. If we go down to the second part of Figure 10-A, you're going to see the buoyancy curve is still the same, buoyancy per unit length, but the weight curve is greater weight than buoyancy in the middle two blocks and less weight than buoyancy in the end two blocks. And finally at the bottom, what you're going to see is a dash line which shows from the left-hand side going up to the end of the second block on the left. That's the shear force increasing, and then because there's more buoyancy than weight, and then it starts to decrease all the way past midships, all the way to the beginning of the end of the fourth block, because the weight is greater than the shear force, and it comes down. And then it goes back up to zero by the end of the sixth block. And that is the shear curve. Now, how is this plotted? Well, it's for each one block length, there's a volume you can calculate. And it's basically the weight time the load, which is the difference between shear and buoyancy. And if we integrate the load curve, you can actually get the shear curve. And then if we follow the shear curve and we add up the weights or the shearing moments, what you can do is you can get the bending moment curve, and that's what's shown in the lower part of Figure 10-8. So going on, the buoyancy curve is plotted in Figure 10-8. Since the body is rectangular and floats at zero trim and has a total buoyant force equal to the total weight of 264 pounds, the buoyant curve can be a straight line indicated buoyancy force of 264 divided by 72, which is the length in inches, and that would be 3.67 pounds per inch of length. And the other thing I'd like to stress here on these diagrams you see, these are not sketches. These are actually graphs that you can duplicate, you can do calculations on based on these units we're talking in the book here. Plotting from the left to the right, it is seen that the excess buoyancy over weight, then the excess buoyancy over weight to the extent of 1.33 pounds per inch exists for the next 2 feet. Finally, the excess buoyancy over weight of 0.67 pounds per inch is observed in the last 2 feet. The excess buoyancy over weight is usually plotted above the baseline, and the reverse is true for excess weight over buoyancy. You may now observe or obtain the vertical shearing force from the load curve by merely adding up or integrating the excess buoyancy over weight or vice versa. The greater the length of the body over which the the buoyancy continues to exceed the weight, the greater the shearing tendency. The logic of this can be seen merely by noting in order for a person to tear or shear even a piece of paper, it is necessary for him or her to exert an excess force over the resistance of the opposite direction with the other each hand. Therefore, in plotting the next curve, the shear curve is, in figure 10-8, the area under the load curve is integrated, summing or adding up, for example, the first 2 feet of total excess buoyancy over weight to the extent of 0.67 pounds per inch times 24 inches or 16 pounds is built up. Thus, at a point, a shear force of 16 pounds exists and is so plotted. Now, a sudden change in the relationship between buoyancy and weight occurs, and the excess weight over buoyancy must be subtracted from the total excess buoyancy over weight at a point 3 feet from the end, which is the middle of this 6-foot long structure. The excess buoyancy over weight equals the excess weight over buoyancy, and the shear curve crosses the baseline. The excess weight over buoyancy is now built up to a point 4 feet from the end where the shear force is 16 pounds is again observed. Then, subtracting the excess buoyancy over weight, the shear curve slants up to 0 again at the opposite end of the body. Now, the greater the built-up of the shear, and the greater will be the bending moment tendency. For example, if you had placed 48-pound blocks in the middle of the floating body instead of 60-pound blocks, the shearing tendency would have been less, leading to less bending tendency. It should be apparent that bending moments are obtained simply by adding up the area under the shear curves. And when we add up the area under a curve like that, it's just integration, whether it's numerical integration or graphical integration. Therefore, in plotting the final curve of figure 10-8, the bending moment curve and the area under the shear curve is integrated. In the scale used, these shear and bending moment diagrams of figure 10-8, each inch ordinate of shear is equal to 16 pounds. Therefore, at a point 2 feet along the baseline, 2 inches into the curve, where the shear ordinate is 1 inch, the vertical shear is 16 pounds. Now, to obtain the bending moment at this point, you must find the area of the right triangle that has the height of 1 inch or 16 pounds and a base of 24 inches. The abscissa on the graph are in foot units. The area of the triangle, base times height over 2, is then 16 pounds multiplied by 24 inches and divided by 2, or 192 inch-pounds. Or, to put it another way, the square inch of area is actually under the shear curve is equal to 192 inch-pounds of bending moment. At the peak of the bending moment curve, the total area of 1.5 square inches lies under the shear curve, and the maximum bending moment is found to be 288 inch-pounds. Now remember, this model we're dealing with is not foot tons or metric tons. It's 6 feet long, it's measured in inches, and the weight units are in pounds. All area between the baseline and the shear curve are now represented a reduction in the bending moment, and the curve once again comes back to 0 at the opposite ends. Now, if there's no moment left at the ends, that means that there's no trimming moment either, because weight equals buoyancy at the ends. If there was excess moment at the ends, then